Welcome to our presentation. This presentation is about study on air quality using variable control chart and QSUM.
All right, so these are our team. Shall we meet them? First, Hadran Atira. Me, myself is Wan Nadib. Then Amirul Akil, Muhammad Umam, then Muhammad Al Farabi.
Introduction of air quality. Air quality is vital for the health of people, ecosystem and the planet. Even small changes in air composition can have a serious effect. Monitoring and improving air quality is important for sustainable future. So our atmosphere relies on ozone, which ozone will form the ozone layer of sunscreen, protects against harmful ultraviolet UV rays from the sun, and prevents increased risk of skin cancer, cataracts and other UV related damage. So for the ground level ozone is a different story, which is act as pollutant and contributes to air pollution and can cause respiratory problems and harm human health. So for dual nature, beneficial in the upper atmosphere but harmful at the ground level, highlights the need to manage emissions while conserving the ozone layer. Variable control chart. First, role of control charts. X bar, R and S chart are used to analyze average and variability in ozone levels. Helps track changes and identify the variation over time, and to determine the most effective chart combination to ensure the accuracy and stability of ozone level monitoring. So for X bar chart with R chart, we measure the average and variability using the range, difference between max and min in subgroups. So it's simple to use, effective for smaller subgroup sizes. And X bar chart with S chart, we measure the average and variability using standard deviation within the subgroups. It's more precise, ideal for a longer or complex dataset.
QSUM, known as Cumulative Sum Control Charts. QSUM is a statistical tool used to detect gradual change in data. Originally designed for quality control in manufacturing, it is now crucial in environmental science, especially for monitoring air quality and detecting contaminants like ozone. Unlike traditional monitoring method, QSUM track minor increases and reduction and detecting early pollution indicators. Early detection of change is critical for treating air quality issues before they worsen, protecting public health and the environmental. Sorry about that. QSUM sensitivity to subtle yet loss-lasting change made its proactive approach to environmental management. Metrics like process capability (CP) and average run length (ARL) are used to assess QSUM charge for accuracy. QSUM sensitivity and dependability make it essential for contemporary air quality monitoring and ozone pollution mitigation. Research objective. First, to determine whether the process is in control of other control for the variable control chart and QSUM control chart. Number two, to compare which is the better interpretation between the variable control chart and QSUM control chart for ozone. Number three, to improve effectiveness of air quality intervention.
Today, I'm going to talk about Chapter 3, Methodology. The data used in this study was secondary data obtained from Kaggle named Air Quality Dataset. The dataset contained 9357 observations with 15 variables, but we only focus on O3 indium oxide with 25 subgroups and 7 samples. We specifically choose 7 hours starting from 12 p.m. until 6 p.m. for the sample size. For control chart, X bar and R chart. X bar and R chart are used together to monitor the mean and variability of the process. So for the X bar, how this works? Control limit calculation is X bar plus A2 multiplied with R bar. For the lower control limit, X bar minus A2 multiplied with R bar. A2 is a constant based on the sample size and R bar is the average range across subgroups. The average X bar is calculated for each subgroup and a center line is drawn at overall process average and control limit are established using the subgroup average. For the R bar, control limit calculation use that UCL upper control limit is D4 multiplied with R bar, and for the LCL lower control limit D3 multiplied with R bar. For D4 and D3 are constant based on the sample size. Move on with our interpretation of S bar and R chart. We make it simple. If the point on the S bar chart are within control limit, the process mean is stable. Similarly, if the point on the R chart are within control limit, the process variability is stable. And lastly, point outside control limit on either chart indicate that the process may be out of control, requiring further investigation. Next, we will be discussing the S-bar chart and S-chart, which are used together to monitor both the mean and the variability of process. These charts are critical for identifying if process is stable or if there is a sign of inconsistency. Let's first look at the S-bar chart. The S-bar chart helps track the mean of the process, showing whether it stays within established control limit over time. For upper control limit, S-bar plus A3 multiplied with S-bar. For the lower control limit is S-bar minus A3 multiplied with S-bar. For the central line is S-bar. This control limit helps us understand if the process mean is within acceptable bounds or if there are any shift or trends. Next, let's explore the S-chart, which is used to monitor the variability of the process, especially through the standard deviation. The control limit for the S-chart are calculated based on the standard deviation of each subgroup. First, we calculate the standard deviation for each subgroup using the formula, where Si is to represent each individual data point in the subgroup, and the S-bar is the mean of the subgroup. Then we calculated the average of subgroup standard deviation, where M is the number of the subgroup. Next, the control limit for the S-chart are upper control limit is B4 multiplied with S-bar, lower control limit AB3 minus with S-bar. The central line is S-bar. Now, let's look at the interpretation of this chart. For the S-bar chart, it helps us to monitor whether the mean of the process is within the specified control limit. If the process fall outside the control limit, it is signal an issue. For the S-chart, this chart helps monitor whether the variability of the standard deviation remains stable over time. If the variability fluctuated beyond the control limit, it might indicate problem with process consistency. Finally, in the both chart, if the any data one fall outside the control limit, it indicates an out of control condition that require further investigation or corrective action. That's all for me. Thank you.
I will proceed with the methodology part for QuizSum. Its purpose is to monitor process performance and detect small gradual shift in the process mean over time. In this study, we will focus on the tabular QuizSum method, which is particularly useful for continuous data. So this shows the formulas for QuizSum calculations. The formula for the upper QuizSum is the observed sample mean minus with the open bracket the target mean plus reference value k, and then we close the bracket and plus with the upper QuizSum value from previous observation. If the sample mean exceeds the target mean, that means the QuizSum value increases, indicating a potential upward shift in the process mean. While for the lower QuizSum values, the formula is open bracket the target mean minus with reference value k, and then we close the bracket and we minus with observed sample mean and plus with lower QuizSum value from previous observations. If the sample mean drops below the target mean by more than the reference value, the lower QuizSum increases, signaling a downward shift in the process mean. And then the C0, upper C0 and the lower C0 are set to 0 as initial values. For the max 0, if the calculated value inside the parenthesis is negative, the QuizSum value is set to 0. Next, the step to construct a QuizSum chart. So the first one is calculate the process mean and standard deviations. Second, we compute the reference value k using k equals to small k multiplied with the standard deviations, where k is commonly set to 0.5. The third one is determine the deviation threshold hash using hash equals to small hash multiplied with standard deviation, where hash is often b4 or 5. Calculate the upper QuizSum and lower QuizSum using the formulas provided earlier. And the fifth is plot the upper QuizSum and lower QuizSum value on a control chart to visualize process performance. When interpreting the QuizSum chart, specific decision rules apply. If upper QuizSum more than hash, it signals an upward shift in the process mean. If lower QuizSum is more than hash, it signals a downward shift in the process mean. If either QuizSum exceeds the threshold, the process may be out of control. And then the interpretation of the chart can be summarized as a rising QuizSum, upper QuizSum indicates a positive shift or increase in the process mean, while a rising in lower QuizSum suggests a negative shift or decrease in the process mean. When the QuizSum value remains stable and below the control limit, it is said that the process is consistent.
Okay, next we move to the results of the study. Firstly, the data is analyzed by using X-bar and R chart. So from the output, figure 1a shows that R chart is shown to be stable since all points fall within the UCL and LCL. The fluctuations are consistent and there is no unusual behavior or pattern from the chart which indicates that the process range is in control. However, for the X-bar, it shows that the average of mean value is equal to 915.25, which indicate the center line for X-bar chart. 0.9s, 12, 16s, and 23 has exceeded the UCL and LCL. Fluctuations appear to be slightly above the center line or the control limit, which indicates that the process mean may be in out of control conditions. Another sample might needed in order to conclude whether the process is indeed out of control.
CP value is bigger than CPK value is meaning that the process is off-centered. The bigger the gap, the more off-centered the process is. If both CP and CPK are less than 1, the air quality control procedure may require improvements in consistency and accuracy.
Next, we move to the X-bar and S-chart. From the figure 2A, S-chart shows no point fall beyond the control limit UCL and LCL, which are equal to 347.12 and 21.76 respectively. The spikes get slightly lower starting on 0.17, which indicate that the process variability is reduced. However, the process standard deviation is believed to be stable and under control. For the X-bar chart, there are few points that fall beyond the control limits. It is similar with the previous X-bar chart except for the UCL and LCL, which are equal to 1133.26 and 697.24. It shows the unstable patterns throughout the overall chart, and the process mean may be in out of control conditions. For the cumulative sum chart, there is a significant fluctuations notable throughout the month. Q-sum lower line shows a distinct spike during 1st to 5th of May and 15 to 20 May. Meanwhile, Q-sum upper line shows spikes around 10 to 13 and 23rd to 25. The chart revealed that the air quality did not stay constant throughout most of the month. However, no point has crossed the control limit UCL and LCL, which indicate that the process is in control. Even though the process is in control, future research is required, as it might be any correlation between the observed fluctuations with climate change, industrial processes, or other factors. The discussion, variable chart is known for its simplicity and easy to conduct. Since the study involved large sample size, which consists 25 subgroups, X-bar and S-chart is more appropriate because it accurately measures variability as compared to X-bar and R-chart. However, it did not respond to small and gradual changes. For Q-sum chart, it accumulated the deviations from target mean over time. It is more sensitive to persistent and small changes in the process, as it involved development of a reference value K and decision limit H. As we can see from the previous results, variable chart does not give enough evidence to confidently conclude whether the process is out of control or in control. We might need another sample to test before we come up with the conclusion. Meanwhile, for the Q-sum, it directly shows the result whether it is in control or out of control. Therefore, Q-sum chart is more suitable for describing the air quality as compared to variable chart.
To conclude, the study compared variable control chart X-bar R and X-bar S with the Q-sum control chart to assess ozone air quality data. The X-bar and R chart showed stable variability in the R chart, but exhibited occasional process instability in the X-bar chart, while the X-bar and S chart performed better than X-bar R, as it accurately measured variability using standard deviation, but it also revealed instability in the process mean. Among the methods, the Q-sum chart proved to be the most effective, as it could detect small and persistent shifts, revealing significant fluctuations in ozone level while maintaining overall process control. And then next is the significance of the study, lies in highlighting the effectiveness of the Q-sum chart as a proactive tool for detecting gradual change in air quality, enabling time interventions to protect public health and ecosystem. The process capability analysis also identifying an off-centered process with CP being greater than CPK and value below 1, indicating the need for recalibrations to meet air quality standard consistently. In summary, the study highlight the importance of continuous monitoring and advanced statistical tools like Q-sum chart for sustainable environment management. Future research should focus on recalculating control limits and validating results with additional samples to enhance air quality assessment and intervention strategy. That's all from us. Thank you for listening.